Tackar. Precis, och vad jag kommer att berätta nu är vad vi sysslar med i vårt labb. Det här på KTH, här, inte långt härifrån. Och jag kanske byta till engelska, skriva allting här på engelska. So what we do in our group, what we really try to develop is concepts, so physical concepts, a new understanding, but also tools to generate, to manipulate, and also to detect light, but light at the quantum limit, at the physical limit, that is at the single photon level. So we're developing new tools to be able to send out a single photon. So if you want a lamp, but operating at the quantum limit, that would only give you one particle of light whenever desired. We're also developing tools to be able to process these single photons. And then, of course, one also needs to detect. So we also develop single photon detectors. So all of this at the quantum limit. And what I find most exciting in this field is that we really have this intersection where quantum physics, fundamental questions that were actually first brought up in the 1920s when quantum physics was taking shape, are now being addressed and are meeting technologies. So we're developing also new technologies, new ways to process information, new ways to communicate that are also based on very fundamental questions. So to generate single photons, the first element, we had to develop a new type of device. And here what I show you here is a nanowire quantum dot. So this, as you can see, this here is 1 micrometer only. Okay, so this is something that is only nanometers in sizes. It is made of semiconductors, okay, fabricated using nanofabrication techniques. And this is then essentially a single photon source. So this is our, if you want, our quantum or nano lamp that will give us a stream of single photons whenever we need. Okay? And we can also make very complex devices. I will not go into the details, what we call the quantum LED, where you essentially press a switch and out comes one photon, one and only one photon. So that's one of the things we're currently developing here at KTH. Okay. What we're also able to do is fabricate advanced devices, complex devices. What you see here is that we are able, these are of course drawings, to take, manipulate, nano-manipulate a single of those nanowires, take it essentially with nano tweezers, and place it wherever we need to build complex architectures. And this takes me to the next slide, where what I want to show you is the type of architectures we're currently developing, where we are embedding quantum sources, single photons in different waveguides, and coupling them, and then we're able with this to essentially build a quantum computer. So what we have here is the building block for a quantum computer, a computer that will not compute with zeros or ones, like we've been doing for the past century or so, but a computer that would take zeros and ones and superpositions, essentially. So that's will definitely give us much more power in computation. And then, of course, what we also need is to be able to detect these single photons. And the human eye is a good detector. So are the CCDs and detectors we have in our mobile phones and everywhere. But they do not operate at the single photon level. If you only send one particle of light on the human eye or any of other detectors, you will not get any detection event. So we had to also there invent new techniques to be able to detect single photons. And what we're using here, what I show you here, is a nanostructure of a superconducting nanowire. So this is also to tell you that we are using all kinds of materials, superconducting, semiconducting, metallic, and so on, and merging all of these together. And this enables us now, what we're able to do here now in Stockholm is really to detect single photons with extremely high efficiency, time resolution, and also a very low noise. And we're addressing also these fundamental questions. Where are the limits? Where are the physical limits? How fast can a detector actually operate? This is an open question that we're addressing. So to conclude, what I want to say is that we're developing quantum technologies. Okay? And these new devices that we're developing give us control over light at the single photon level, at the physical quantum limit. Okay? That's one thing that we're currently developing. And this will also not only enable new fundamental experiments, but also will have applications in communication, for data security, for instance. I'd be happy to discuss this one. Also computation with higher energy efficiency. You can, in principle, devise a computer that operates at the highest possible energy efficiency. okay, good for the environment, for instance, and also sensing, so detecting things with the highest possible resolution that is possible, again, limited only by the laws of physics. Okay. So what we see here is really this opportunity, or opportunities, I would say, for a quantum technology initiative, and this is something we're initiating now in Stockholm, to bring together fundamental science and industry. So thank you.
Thank you.